Good morning, everyone. It is my absolute honor to welcome you all on this two-day national conference on multidisciplinary approaches in network and computing, jointly organized by the Department of Computer Science and Engineering and the Department of Mathematics. I am Manasi Sober, and I have the privilege of being your MC for today's conference. We have privilege to have among us distinguished speakers who will be sharing their valuable insights today. To begin this enlightening journey, we have Professor Diganta Mukherjee sir from ISI Kolkata, who will be delivering the keynote addresses on his topic Modeling Market Microstructure with High Frequency Data. So I request Ms. Kankita Borua to kindly present sir with a fulam gamusa and a memento. Please, all of you, give a round of applause. Sir, now I request you to come up on the stage and deliver the keynote. The stage is yours, sir.
Okay, so should I start? Right, so very good morning. It is always a pleasure to come to Dibrugarh. And a big thank you to Kaushik for organizing and inviting us to Dibrugarh again. And I can see my friends. That's always a big plus. So this conference is supposed to be about networks, around networks. So what I will talk about today is how we use the network models in financial data. So the context is a little different. So I will spend a few minutes talking about what we are going to work with, as in the financial market, what are the things that we look at, and then we will see how the graphical models or network models help us in understanding this situation. Okay, so first a little bit about the situation. This is ongoing work with my students Shaurajyoti and Orpon. Actually, Shaurajyoti is currently doing his PhD in ISI, so it is part of his PhD work. Sumanto is one of our ex-students who is now teaching at Cornell. So that's our team. So first the context, a little bit about the financial market and what we are actually looking at. So you see, once upon a time we used to think of stock markets as places where people shout a lot. They wave sheets of paper for selling stocks. Some people come and they also shout to buy stocks like that. So those days are gone. So you do not see people shouting in any stock exchange anymore. Everything is electronic. So what you do is you sit in office or at home, you log in to the stock exchange website and look at the prices on offer for different shares. If you want to buy, you click the mouse and that's it. So as a result, what has happened is the amount of transactions have gone up very, very fast. Earlier people had to shout, right? So shouting takes a few seconds. Now people click mouse and that can happen from 20 million terminals at the same time. So you have so many more transactions happening every second, every minute. So that has created a very big and very complex data which we call the high frequency trading data. In fact, some people call it ultra high frequency because now we talk about fractions of seconds. So it is like how fast we can use the internet, how fast we can use our computer algorithms to do buying and selling of shares from anywhere, literally anywhere. As soon as we have such a situation, people also have new strategies because we are very smart. People design new strategies to use that information to find out what to sell, what to buy, and also when to sell, when to buy. So the strategies have also changed looking at the new technology, and these have resulted in algorithms, computer programs being created which will do the trading on our behalf. So now many of the tradings are not done through humans clicking a mouse, but actually a computer program doing it for us. So the computer program knows exactly what we want, and it will do it obviously much faster than we can because we have to physically click the mouse. So if you actually see this kind of data, this data will look very much like the telecom data that you may have seen, where mobile telephone calls are being made all across the country from so many crores of handsets. Every one of you at least have at least one in your pocket right now. So this data also looks like that. So every minute there are so many trades that happen. So what are we going to actually find out from this kind of data? Let us think of 1 minute of time. You can even think of 1 second, but 1 minute is more or less okay. Think of 1 minute of time. Within that one single minute, there are 60 seconds. Tradings happen multiple times every second. But it may not be that every second has some trades. Maybe there are 5-6 seconds where there is no action, and then in the next 2-3 seconds there are 30-40 trades. So sometimes we have a lot of action and then a little bit of slow motion and then again a lot of action. So it's like an action movie. So you have some action and then there are some songs, some outdoor shots, and then you go back to the action. This trading in that minute also tells you how fast the shares are changing hand. How many shares are being sold, how many shares are being bought, which we call volume. So for us, the information that we want to analyze is over a minute, how much volume is changing hand, at what price. Not only that, whether that change of hand has happened more or less uniformly over that whole minute, or is it like bursts of action in 5-6 seconds, then some slow motion, and then again another burst of action. Because if it is uniform, then it reveals one kind of pattern, one kind of information to us. If it's bursts of action, then we have a different kind of information. And accordingly, we can change our own trading strategies to make profit from this market. So that is the background. How do we interpret these things? As I already said, bursts or uniform. So the objectives pointer. No, no, no. Any pen. Do you have a pen? Yes? Okay. So, what are the objectives? The objectives are, we want to understand how the price, volume, these variables behave, which we call microstructure. Why microstructure? Because we are looking at the stock market structure at a very molecular level, very short time level. We call this microstructure. And if we can understand the pattern at this microstructure level, then we may be able to come up with a model so that we can get very rich, hopefully. If our model works very well, we can buy and sell successfully and become very rich very quickly. So what is the data? Now here, unfortunately, the data that we have in a structured manner is not from the Indian stock market. In the Indian stock market, such data is available, but getting access to it is harder. Surprisingly, this New York Stock Exchange database was easier to access. So this is the data that we use. So what is the data like? Stock market, if any of you know about the stock market, it is open usually in India from 9:30 to 3:30 in the afternoon. In the US, in the New York Stock Exchange, it is open up to 4. So it is 6.5 hours every day. We have data on trades, buying, selling activities. The first thing that I need to know is the timestamp. Exactly when the trade happened. And when I say timestamp, it is like hour, minute, second, and then decimals also, because things are happening very fast. At what price it happened, and how many shares were changing hands. Timestamp, price, and volume. That is the data. But it comes in a large volume. What do we want to do? We want to first understand empirically, looking at the data, what is the information hidden there about patterns. It is important to understand that there will be big gaps and then lot of activities within a short time. So this irregular pattern itself has information for us. So along with this volume and the price, we are also interested in the duration. So what is duration? Duration is the gap. And this data we are going to collect, we are going to analyze and create a graphical template. So that graphical template is what I am going to show you today. There is also this additional model that might come up. We have a model, but I am not going to look at the model because the model is more technical. It is more interesting to look at the graph. So that's what I will focus. So I said 1 minute of time for me. So all the trades, all the actions that happens within that minute is aggregated. I collect them all in an array. So for each 1 minute interval like this, I have an array of trades. What am I storing? How many trades happened in that 1 minute? I call that NP. What were the prices at which shares were bought and sold within that 1 minute? It is this array. And then the volumes. As I said, we always look at price and volumes. The point you need to remember is that how long the array is, that is variable. In a particular minute, that NT could be only 2 or 3. when there is low action in the market. In a different time of the day, within that 1 minute, that entry can be 40, 50 when there is high action in the market. So the length of this array will also depend on how many trades happened. So what am I going to do with this data? So we are going to look at these formula. Yes. Only one second. So what are we going to calculate with this data? First, we want to understand how much fluctuations happened within the minute. Fluctuation in terms of price. So that fluctuation we capture in different ways. We can look at something called variance. If you are from the mathematics department, it will be very familiar to you. If you are from computer science, maybe not. If you want, I can write the formula, but let us discuss this first. So it is just a measure of fluctuation. Price change, this is the end of the minute, the start of the minute. The first trade that happened, the last trade that happened, what was the change? Sometimes these changes can be positive, price is going up. Sometimes this can be negative, price is going down. So we also look at the absolute change. And this is the mean of the price changes. Yes. No, you have to fix one share and then look at it. For different shares, you have to do the same calculation with. So I will illustrate using one share, but you can do the same thing for other shares. So these are the different fluctuation measures that we look at. What else? So a little bit of statistics possibly. We also look at how the price from that first trade influences the price on the second trade, how it influences the price on the third trade, and so on. So in statistical language, this is called autocorrelation. Autocorrelation is nothing but correlation with myself. So how my past is influencing me now. So how past price is influencing the next price. So we look at autocorrelation of the prices. We also look at the autocorrelation of price changes. They may have different meaning. So these are all calculations based on the original price array. We also have the volume array. We also look at the following things based on the volume. Total volume, average volume, so average volume per trade, and a weighted average of price where the weightage is as per volume. Why are these things important? Because I already mentioned, remember that the pattern, whether it is uniform or not, is of interest to us. If the pattern is uniform, then most of the time the volume trade will be around this average. But if there is too much fluctuation, then sometimes there will be very small volumes and a few very large volumes. We will get to identify that immediately. And this will tell us whether bigger trades changes price more or smaller trades influence price more. So we give a weighted average. The weightage comes from volume. So volume is the importance and target is my price. So there are different ways we can look at it, but these are more or less meaningful, simple measures. So is it okay so far? Because this is a new context, so if you have anything that you are not clear about, please ask me. I have just described the data. and I have also described what are the formulae that we are using and why we are looking at this particular formula. We are looking at price and its fluctuation, its relationship with itself. We are looking at volume and its fluctuations, as well as a volume weighted price average, so that I can give more importance to larger trades and so on. So these are the variables that are of interest to us, and we feel that these things combined together can tell us a lot about how the market is behaving. And of course, I have just described the 1 minute data. This we can do for every minute, for every consecutive minute throughout the day, throughout the week, throughout the month. The data will become larger and larger, but it is the repetition of the same objective. As also Surojit sir just mentioned, that we do it for each company stock, each company share, but we can then do it for 50 companies shares. We have to repeat this exercise 50 times. So what we always do is we first try to learn about whether our model, our technology is at all good enough by looking at one stock, one company's share closely, looking at a small amount of data, maybe of 1 day, and if we can find meaningful conclusions, meaningful inferences from that, then we can always generalize, because generalization is easier. You just run the program on more data. Yes? 1 minute level. 1 minute.
Can you extend this in timetable to for 5 day 1 day?
No, of course you can, but you see, our focus is on the assumption, no, not on 1 minute. The focus is on the assumption that things are happening very fast. So if you aggregate over the whole day, then you will maybe lose the details within the day. So we want to focus, that's why it is called microstructure. So I'm trying to, look at it through a microscope. So why should I look at the whole day? In fact, you should have asked me, why not do it for 1 second? Even that is possible. Okay, so now I have to talk a little bit of statistics. How many of you know this term? This one. Similarity degree. You mean in the graphical sense? What is similarity degree?
That means a particular representation of the relation between the event time and the lag time itself. Can some kind of similarity degree be found?
No, but is there a formula?
Yes, we have some kind of formula. We can take some kind of
So if you tell me the formula, then I can tell you whether it is something like or something else, because I don't know the definition formula that you are talking. No. PT is my data. PT is my data. See, PT is there. This is my PT.
in our computer science technology, to design some abstract project, we use some model. So in that particular case also, if we take a PT, if we consider a PT, then this formula will be calculated.
If you give me the data, you can calculate.
Yes, sir. You are giving the example of the trading data.
This is trading data.
If we take it for other kind of data also,
Any data, any time series data, if you have the data, you can calculate these things.
I am comparing it with the machine learning model actually for.
No, but what is the formula within that machine learning?
No, first we have to take the data,
Yes.
then we can use the formula.
What is the formula? So, what is the formula? Unless you tell me the formula, how can I answer?
We need only the time parameter in that formula.
But what am I calculating? See, machine learning is a dangerous word to me, because machine learning often means that I give something to the computer does something which I don't know what, and then something comes out. Is it something like that? I am very comfortable with writing my own code in C or Python, then I know exactly what is going on inside the computer. Okay, so how many have heard this term principal component? You don't need to know the definition. I am not going to ask you the technical thing, but the idea, what does it do? No one. Okay, no problem. So then I think I will use the board. So I have described some formula that we are going to use as information. Those are my variables now. I had the original price and volume data, but then I have calculated some variations, some autocorrelations, some averages. So those are my new variables which I feel will give me information about the market. There are 8-9 of them. Now all 8-9 of them may not be equally important for my analysis. So what I want to really do is identify which of those formula is giving me more information, so I will focus on them, and if some other formula gives me little bit of information, I may even ignore them. So that is a principal component analysis without going into any mathematical details, that allows me to find out which are the more important variables. So it's a variable selection method, which it allows me to find out the more important variables. What is the advantage? The advantage is I had 8-9 things to think about. It is harder. If I can bring it down to 4-5 things, 4-5 variables only, I will be more comfortable working with fewer equations, fewer variables. It makes my job easier, and I don't want to compromise too much on information, because whenever I give up something, I also lose something. I will lose some information, but if the information I lose is a little bit, then maybe I'm happy enough. I will show you some pictures which will help us to understand the technique as well as how we are using it. Yeah, this is good. So all the definitions, yes. No, he's coming forward. Good. Very fine. Yeah.
So sir, like when we perform principal component analysis from the original distribution of the features or the variables, we usually retain a set percentage of the total variables. So like, can you tell us like what percentage have you? Okay, sir. Oh.
Okay. So this is principal component analysis in picture, which is so much nicer. So we had all those variables defined earlier. Actually, we had 11 of them. So with my original price and volume data, we calculate 11 things. Oh, this one is not working. This is better. Okay, this is better. So you can hear me now? So principal component analysis is like this. I know that the total information I have is contained within the 11 variables I have calculated. That is my total. So that is my 100%. So this is 100%. But how do I reach 100%? Do all of them contribute equally? Usually no. Principal component tells me their order of importance. This picture here is known as a scree plot. This is known as a scree plot. It tells me what is the contribution of the most important one, which is 32%. Then it tells me what is the contribution of the top 2, which is 50%. So you see, with 11 things I have 100%, but only 2 of them gives me half the information. But I am not happy with only 50%. I want more, as he was just saying that, well, how much percentage should I target? If I go up to 4, I have 73%. It's like almost 3/4. And so these numbers progressively gives me how much additional information I get when I add the next important variable. And you can obviously see that after a point, the increment, the extra, is very small. So this is what principal component analysis allows us to do, to choose a stopping point. A stopping point could be in terms of percentage here, that okay, I have reached 90%, let's stop. That could be a rule. Or it could be that as soon as it slows down, as soon as this plot slows down, it is coming down fast, then it slows. As soon as it starts slowing down, I will stop. Then I will stop maybe here. There are different rules, and these rules are not mathematical rules. These are all thumb rules. But objective is the same. I want more bang for the buck. Fewer variables, retaining most of the information. That's what we use. Is it clear now? So they are getting ordered by this analysis in terms of importance. I will supply them in the original order, whatever I have formulated and calculated. This algorithm tells me who should come first. So not only the 32%, it will also tell me who is the 32%. Of course. So that's what I am going to show. So is it okay? So this is what we do with the scree plot. Now these are the steps. So first you see how the contributions are ordered in sequence, starting with the most important one. Then, as I said, you can look at where it starts slowing down. When it starts slowing down, it could be a good point to stop, which is called an elbow. You see my hand, elbow. So upper arm is going down fast. The lower arm is not going down as fast. It is slowing down. So that elbow point. From that, we decided that okay, we can take 4 or 5 of the top variables and stop. Then I will only need to process 5 things at a time and not 11 things. So that is the principal component strategy. There is a second strategy that we also look at, which is I have these 11 things and they give me some information, but not all of this information is separately coded in these different variables. Some of the variables have a part of the same information and a little bit of a different information, which means these variables, they also become correlated with each other because there is some common pieces of information coded into different variables. How much is that? So this is a correlation heat map. It has the correlation numbers but also colors, where a color which is darker on the red spectrum is a high positive relation and a color darker on the blue spectrum has a high negative relation, because it can be both negative and positive. By definition of the formula, it has to be between -1 and +1. 0 is no relation. Both +1 and -1 are strong relation, perfect relation. So this also tells me similar story, that I really need not select all the variables because they have common pieces of information. So let us try to pick up those which gives me separate information. So how is that separate information used? So this is the second strategy. It has got its own narrative. We look at the correlations, we find out which ones have strong relation with each other. Natural candidate is then, if two are very strongly related, maybe I need to take only one of them, because the other one would be a close copy of the first one. That's another way of reducing number of things that I have to work with. But there is a better way, more automated, better way of doing this, using a heat map called a partial correlation. Partial correlation is where I can highlight the independent pieces of information. So this is the partial correlation heat map. So these measures are all now readily available in standard Python notebooks, Jupyter or Panda. But before you start using them, I would need you to go to the Department of Statistics and learn the definitions. So don't use them unless you know them. So these are like spices. They make your food very tasty. But if you don't know what is the right combination, you can get diarrhea. So don't do it. So this partial correlation also gives me, in a smarter way, same kind of information. So these are details of how we select the variables. That is not so important now, because I will tell you which variables we are going to work with. I am just trying to highlight the usefulness of these strategies, using principal component, using correlation, or using partial correlation. They have different interpretations, different advantages. So in a real life data analysis, we normally do all of them to see whether our intuition is matching across techniques, because each technique has some advantages and of course some shortcomings. No technique is perfect. So this is our final choice. We had a lot of variables, and then we came down to a smaller set. We come down to a smaller set. They have different things. They have averages, they have variability, they have autocorrelation. But whenever there is a repetition of information, we try to drop one, keep the other. So we try to find independent sources of information, and we have finally 6 candidates chosen. These candidates are the same as before. I didn't use symbols probably earlier, but you can see that these are related to the variance, the total volume, the autocorrelations, and the absolute changes. So these, in our opinion, using the techniques that I have just described, gives us maximum information with a small number of features. So in computer science, you are more used to talking about features. These are features. We call them variables, but you can call them features. Now I will tell you something more statistical, but probably I will skip the slides and show you on a picture here. My drawing and handwriting both are terrible, so please excuse me. So how we study relationship? So it's not like not only like human relationship. We study relationships between different features through some statistical model. The most common statistical model for learning about relationship is known as the regression model. So the regression model is typically used in all sorts of relationship studies. But sometimes we need to be a little more clever with these things, because what happens is sometimes we have variables who are measured in different scales. They may have very diverse kind of features, and putting them together in a regression model might be very difficult to interpret. You can mathematically do it, but interpretation can become hard. So we need a little bit of variation on the method. Also, there are times when, after all this careful screening and everything, we still have some instability in the relationships among the features. Then also we need some modifications of the regression methodology. Regression methodology is still the foundation, but we need to build on it in a smart way. So the structure that we have used is known as lasso. It is a variation of the regression method. So I skipped those slides. They are not really necessary, but I am going to tell you what it does. Lasso essentially tries to highlight more important relationship quantum and suppresses less important relationship quantum. Why is that important? See, we have these 6 things, 6 features here, and you know that if there are 6 features, then there are 15 possible relationships here. That is 6 choose 2. For a human eye, looking at 15 relationships together and interpreting them is very hard. So lasso helps us to identify which of them are actually big. So it will highlight only those big relationship quanta and suppress the smaller ones. So when I see the relationship, so now you see, this is where we start talking about graph. This is where we start the graphical analysis template. Because if I have 6 objects here, I have this graph. There could be 15 edges. I have drawn some of them. This is our template in preparation. And if I have all 15 present here, it will be difficult for me to assess visually. I want to assess visually. I will show you pictures. So what this technique helps me to do is, if some of these have smaller strength, the algorithm will erase those links. It will only retain the stronger links, so that when I look at it visually now, there are fewer edges and it is easier for me to understand the relationship dynamics. Is it okay? All of you are familiar with graph? Graph you have seen, right? So objective is, if I have many nodes, there could be many edges. So I want to suppress the less important ones, highlight the more important ones. That's the objective. Yes. I'll tell you. So now, as prompted by Surajit sir, right now, I am going to tell you how the strength is assessed and which edges should remain. These were our starting variables, so we have so many edges possible. 6C2. For each pair, what we do is we perform a test of hypothesis to see whether the relationship is really strong. And what do we mean by really strong? This is our usual regression methodology. If the relationship is so strong that the p-value is less than 5%, we call it statistically significant at 5% level. If it is really strong, we keep it, otherwise we erase it. And each edge is then labeled with the p-value. So p-value itself shows me the strength of the edge. The smaller it is, the stronger the edge. So remember, it is the other way around. A big p-value is bad, then it will be erased. A small p-value means it will be retained, and smaller, stronger. So we apply this technique. What do we see? So this is the interesting part, hopefully. This is data for just one day, and it is not mentioned here, it is mentioned earlier somewhere, that the data we are using is a popular stock, a popular company. All of you know the name, IBM. Okay? And now you can see that we can do this for other companies, it doesn't matter. I have to create the same data structure and recalculate, but we wanted to understand with one company first, and obviously a company which is very big, very well known is a good illustration. So we took IBM. This is one single day from morning 9:30 a.m. to 4 in the afternoon. Every minute is analyzed. So we have 330 data points. No, 390 data points. I think 6.5 hours. So it's 390 data points. We do this calculation using this variation of the regression model called lasso. We keep only the big ones, and now you see this is our strength measure given here. These are p-values. So this 0.0 means it is 0.000 then something. So we do not show that long number, but that also means that this 0.02 is actually weaker than this 0.0, because remember, p-value smaller means stronger. So this is what we have for one particular day, relation between the 6 features that we have selected, where the weaker relationships, all the other possible edges here, they have been erased because they are not important enough. Now, what do we do with this? This is just one day, one stock. So what? What about tomorrow? So I did this yesterday. I do it tomorrow. I can do it day after tomorrow, and so on. You see, this is what we are doing. We are looking at the change in this graph over each day, and it is changing in the sense which edges are important on a particular day. That is not the same as yesterday and not the same as tomorrow. But then we have this other extreme problem. I have a visualization, nice pictures, but there are too many of them, too many pictures now. So if I want to analyze, say, 1 year data, how many pictures will I have? And it's a trick question, because I am not asking that there are 365 days. How many pictures will I have if I analyze 1 year data in the stock market? Any idea? Do any of you know which days of the week stock market is open and if it is closed ever? Any idea? Huh? Monday to Friday, right? Monday to Friday. So how many days in a year? How many days in a year? No, 365 is the calendar day. Stock market is not going to be open for 365 days. Huh? Around 260. Actually, what we get is around 250, because there are some public holidays, right? The stock market is always closed on 15th August. It is closed on 26th January, and some other big holidays. So it's around 250. 260 is the just number of Monday to Friday, but there are then some public holidays. So if I want to analyze 1 year of data, I will have 250 graphs. That's too much. Again, there is no visual way I can analyze this and find any pattern. So what do? We do a very simple thing. We try to check the following question, that for each possible edge here, there are 15 of them. On each day, some of the edges appear and the others don't. I count, if I look at it over a year, on how many days a particular edge is present. So if an edge is present on most of the days, that means it is really important. Most of the time, that link, that relationship is significant. So this is just our description of what we just did. So for a particular day, we did the lasso, and then we try to find which ones are consistently present. So this is our, again, simple relation. So this is a second stock, because we are doing it with 3 stocks actually. This is with Apple. So we try to see for which stock our relationship measures are significant most of the time. If you look at this, I showed you the partial correlation heat map earlier. If you look at the partial correlation, then between these two, so this is one possible edge. I am looking at one possible edge. Every day I am seeing whether it is giving me a significant value or not, and I am plotting the frequencies here. So for example, over the whole time period, these two variables had a partial correlation of 20% on 14 days, 14 many days. It had a relationship of 30% on 7 days. So it goes like that. So I am counting. So if I see a lot of height here, tall bars on this side, far away from 0, because 0 is no relation, remember. 0 means no relation. So farther away from 0, stronger the relation. And if the bars are taller here, I will feel that this edge, this particular edge is important. Simple logic. No formula, no mathematical details required. Just count. This is for the original IBM data. So I showed you the IBM first. Same thing for IBM. Now you see this is even more clear. Everything is far away from 0. So the minimum is here a little bit, but then most of it is 20% to 40%. The whole bulk of the data, which is very good, which means the relationship is really important. It's not only on a particular day, it is over a long period. Most of the days I have a strong number going around. This is again Apple for a different pair of features. IBM for the same pair of features. So what I am showing you is 2 shares, 2 companies and 2 edges. So IBM is one apple is another, and I am looking at this age over the days and this age over the days. It is just a counting method, nothing complicated, but it gives me a clear picture. How much consistency? Yes. Yes, of course, they are the same. See, strength of relationship is in the magnitude. So a minus of 0.9 is also very strong. It only acts opposite direction, but it is a strong relation. A plus 0.9 strong relation acts in the same direction. Both are important. So what I don't want is numbers close to 0 on either side. That is the insignificant part. So if I get things here or I get things there, I will be happy. No difference to me. So that's the outline. That's what we have done. So basically, we create graphs like these over days for different companies, and then we try to find which ages are consistent by simple counting. And that actually tells you, if you look at it closely, exactly which ages I need to retain in my final model. I am not going to talk about model because then we'll get into more technicalities, but this is our way of using a graphical model, a graphical structure, to identify what we call microstructure features in the financial market. So that's it. Thank you. And these are some of the references. Yes.
It's a micro.
So whenever we look at like traditional stock markets, sir, we see that liquidity is always continuous.
What is a traditional stock market?
So stock market where the demand and supply is quite like fluid. Like let's say if the demand increases slightly, supply will also adjust accordingly. No?
But what is traditional about it? That is always true.
So sometimes marketers who are looking into the liquidity pool, they manipulate it. No? So if someone
That is also using the demand supply imbalance only. The fundamentals are the same. How you use it, you see, you know how nuclear reaction works. Whether you want to build bombs or create power supply, that's up to you.
So, but the question is, sir, so like market microstructure model often assumes that liquidity is a continuous like
No.
function.
No, it doesn't.
So it doesn't.
No.
So then what is it, sir? That like exactly?
So do you really know what liquidity is?
Yes, sir. So when there, let's say that a stock is getting decreased, a seller is ready to sell that stock, particular stock at a certain price, and the buyer is ready to buy at a certain price. So the difference between them says about the liquidity of that market.
How?
So,
How?
so let's say you want to sell a stock at like 150 rupees.
No. I am asking you the mechanism. I know it happens, but do you know how it works?
No, sir. Exactly, I don't know, sir.
So can I have 2 minutes? Okay, so when he says liquidity, I don't have the corresponding slide. I could have brought it, but I didn't. So in the stock market, at any point of time, inside a database like this is created. This database is known as the order book. So what is the order book? The order book lists all the buy demands and all the sell demands. So these are demands. This is not trade yet. So when I want to buy something, I click the mouse. My order goes here. How is it placed? Those who are willing to pay the highest are placed at the top, and then it goes down in that order. So on the buy side, prices will be decreasingly ordered. The highest will go first. Okay. The sell side, it is exactly the reverse. If I want to sell, the cheapest offer will go first. That is how the data structure internally is maintained. And whenever there is a match in prices here and here, if there is a match, then a trade happens. Then a trade happens. What is liquidity? Liquidity is how much time do I expect to wait after I place my order. If this particular company share is traded very frequently in the market, almost all the time, then I would expect that if I put an order here, there will be very quickly a match found on the other side and my trade will be completed. So the faster it happens, I will say that the stock is more liquid. Now ask your question.
Hello. So sir, I had doubt regarding that only. So I thought that liquidity is continuous function of supply and demand. So sir, when we look at like empirical data.
So again I will ask you, what do you mean by continuous function?
So the demand, let's say the demand is increasing suddenly. Let's say I want to like buy a stock and that stock is very limited. So sir, the supply has also to be adjusted accordingly. Like
Why would the supply adjust?
Because that particular stock is limited in nature.
The total number at any point of time is fixed, but not all of them are coming for trading in the market. Okay, maybe only a small fraction. So the important part is whether there are enough parties planning to buy, and at the same time another large group of parties are planning to sell. That is where this matching will happen faster. So if there is a huge demand, everybody wants to buy, then this side will become bigger.
And if everybody
Do you have sufficient matching orders on this side? If yes, then matchings will happen, trade will happen. If not, they will have to wait. How do they do that? When they don't have a match, they keep increasing the price. Why? Because then on the sell side, somebody may get interested to sell. Okay, I am getting such a good price, I will sell.
Thank you, sir.
Yes.
So, sir, I have two questions. The first question is regarding the data set. Based on the companies you have listed, I guess you are using the NASDAQ data.
No.
Which data, like which exchanges data are you using? Okay. So, sir, for this, like we have certain packages such as the Y-Finance package for extracting data. So, can you tell me firstly a bit about how you have extracted the data?
No. This data is proprietary. This is not free.
Yes, sir. So,
you
like.
need to have a membership.
Right, sir. So actually, when I was working on a stock trading algorithm, so in my case, I was using the Y-Finance package, which directly collected the data from the NASDAQ listed companies. These companies are also listed there.
But Yahoo Finance data that
Yes.
you get publicly, that is not the kind of microstructured data that we are working with.
Okay.
That gives you maybe one quote every minute or one quote every 5 minutes, something like that.
So actually, I had collected for a period of 15 years.
No,
so
what is the time gap between each quote?
Sir, it's divided into a sliding window approach of 60.
No, the data set.
Yeah, it's a data set only. So it's stored in a CSV file. It starts from the first of the fiscal year 2010. That's April 1, 2010.
What is the first observation timestamp? What is the second observation timestamp?
Yeah, there's a 5-second difference, sir.
5 seconds.
5-second difference. So
This is continuous.
This is continuous.
All the trades.
Okay, sir. My second question is, by nature, we assume since you are working on time series data, So by nature,
This is time series.
yes. So by nature, we assume that time series has to be continuous, or rather, we should say sequential in nature. Is there any other parameter that we can use to ensure the complete sequence distribution when we are compiling the data or say processing the data?
I did not
Sir,
understand.
means by nature, when we are working with time series data, so
Yes.
we normally carry an assumption that time series data has to be sequential in nature.
It has to be. It is time series.
Right, sir. But is there any other parameter we can use to ensure that it is, when the processing is done, it is always done in sequence? Like, sir, there might be certain features when we are using, like when we are in machine learning, if I say, when we are using training and testing.
So do you know what is going inside your black box?
Sir, yes, sir. So initially, like, as per, this is based on what I did. So based on that, when we perform the split, sir, if we want to evaluate or achieve optimal accuracy, then, sir, there are
How
certain,
is accuracy defined?
sir, accuracy is defined as the ratio of true positives to the total number of predicted
But what is
positives.
your model then?
So LSTM.
LSTM.
Actually, sir, it's just formulas.
No, okay. LSTM I am familiar with. That's okay. LSTM is a time series model, so it is already assuming the time series property of the
Yes, sir.
data.
Sir, regarding that only, I had one more question. So, in my case, I had, as I said, I had also implemented a sliding window approach. So
That is fine. That is good.
so, sir, does that change the, or does that enhance the performance or optimization of the algorithm, or say just the method? Let's not get into algorithms. If we just consider scenario.
You can.
Yes, sir. So, like in that scenario, based on the reviews or based on the techniques that you have implemented, do you think that applying a sliding window approach would enhance the output?
Sliding window will always enhance because
Okay, sir.
you are using information optimally and not having too much of the past in the model. But then you also need to change the length of the window
Yes, sir.
and see which one works the best for you.
Definitely, sir.
That you have to try yourself.
Sir, if you allow me, can I ask one more question? Okay. So, sir, like when you collected or say generated the data set, so, sir, were there any specific technical indicators that you use, such as adjusted closing volume or?
No. These are the. There is no closing volume. We are looking at every single trade.
Right, sir. So, did you select any particular, like we select a target variable or target column based on which the other features are computed? So, say like estimated
no.
moving average.
See, you are talking about some kind of a regression analysis.
Yes, sir.
But first, you need to decide which are the important variables to be put in the model. So I have not got into the model yet. Maybe. Oh, yeah.
Okay.
Oh,
Okay, sir.
Yeah,
Thank you.
thanks.
Thank you so much, Professor Mukherjee sir, for that insightful keynote addresses. Your words have set a tone for an engaging and thought-provoking conference. Next up we have Professor K.S. Mallikarjuna Rao sir. I would like to request you to come up to this podium, and I would like to request Ms. Kankita Borua to give sir a memento and a Fulam Gamusa as a token of appreciation. Please give them a big round of applause. Thank you, sir. The stage is yours, sir.
It's already in the full screen mode.
So actually, it doesn't support full screen. It doesn't support full screen your PDF.
It's happening.
So
Okay, then it's happening. Yeah, sure. Yeah, first of all, thank you very much to the organizers, Mr. Kaushik Das and of course my friends Rajit, who have given this opportunity to speak to you. And of course, it's always nice to come back here again and again. And of course, I also like to forget many things while I come here. Okay, anyhow, so let's. So I'm not specifically pointing out any specific problem or anything, but I just wanted to introduce you to this area of network games through, of course, some couple of examples. Okay, so I think let's walk through it. I'll try to first explain every term that I'm using. Okay, so this is a brief overview of whatever I'm going to speak, but anyhow, we'll see. Okay, so first let me introduce you very briefly this game theory. So game theory is the study of, I think many people may be familiar with this subject, but let me give you a very brief idea of this. So game theory is the study of conflict and cooperation, and its subject is supposed to have, people believe that the von Neumann's min-max theorem is basically the starting point. Of course, even before von Neumann, there are a lot of ideas by Emil Borel, Cournot and many others. But then the proof of this min-max theorem actually triggered the entire development of the subject. Now this is, of course, there are two aspects. One is called cooperative game theory and other is non-cooperative. Of course, in my talk you will be seeing the non-cooperative part, and it has applications in multiple fields. Okay, very briefly, there are n players, and each player has some strategy space. That's Si is for the player I, and there is a payoff function pi I, which is a function on this tuple S1 cross S2 cross Sn. It's a real valued function, and then each person is trying to maximize his own payoff. So, and Nash equilibrium here is again tuple S1 star S2 star Sn star, such that this condition pi I S star is greater than or equals to pi I S minus I star comma Si. What it means is that unilateral deviations are not profitable. Suppose everyone else's fixes, for me deviating from this strategy to something else is not profitable. So that's basically the Nash equilibrium. So this is the brief idea of the game theory. Let's introduce the network. Again, being in the computer science department, this particular thing, many people may be familiar with networks. So again, I'm giving you only very brief things. So network, there is a finite set V, and each elements in this V, we call them nodes, and a subset E of V cross V, and each point in E, you call it as an edge. Now there is something called undirected, which means if I comma j is inside E, then j comma I is also inside. Okay, if that happens, it's a undirected network, and otherwise it is directed. And also right now we assume that there are no self edges. In fact, in most of the part we will look at undirected graphs over here. Now, another most important concept in the networks is this eigenvector centrality. So the centrality measures are very important, because given a network, which node is important, how do you really specify? So for example, if even if a friendship network, if you take it, if I have more friends, that means I'm better, like that. This is known as a degree centrality. Like that, there are many kinds of centrality, but the particular one I wanted to talk about here is what is known as eigenvector centrality. It essentially says that you assign a number to each node, which is nothing but proportional to the centralities of all its neighbors. So okay, a neighbor I did not define formally. Suppose if I comma j is an edge, that means j is a neighbor to I. So look at all the neighbors. You are assigning these numbers to each of them, and then it should satisfy that my centrality is nothing but is proportional to the sum of the centralities of others. So that's essentially boils down to this eigenvalue problem. Ax is equals to lambda x, where A is adjacency matrix. Adjacency matrix, again, once again, I didn't define that. Adjacency is Aij is equals to 1 if there is an edge between I and j. Otherwise, this thing. Now, another important thing I wanted to say that this adjacency matrix here is a non-negative. It has non-negative entries, and then one of the very beautiful theorem from linear algebra which says that non-eigen all the if the matrix is non-negative entries, there is always an eigenvector and eigenvalue, and corresponding to that eigenvalue there is an eigenvector with all non-negative entries, and of course this eigenvalue is basically the dominant. That means it's a real value. So that's a very important result, and this eigenvalue eigenvector is a very important, for example, in this Google page rank. This is one of the most successful, and we are not talking about that. Of course, that result is known as a Perron-Frobenius theorem. And then Kac-Bonac's centrality is essentially the eigenvalue centrality. What it does is this particular thing. Instead of directly taking this Ax is equals to lambda x, you are looking at x is equals to 1 over lambda Ax plus beta. Basically, for each edge you are giving certain value so that none of them are zeros. So it avoids certain interesting facts. So this is the Kac-Bonac's centrality. Now let's get into the network games. Okay, so once again you have a network, and now the player, basically this network is nothing but there are set of players. All the players are connected by this network, and we are all these people who are on this network, they are all playing. Now every node is now a player. Each player has a choice to make, and those choices are again the choice sets are given by this S1, S2, Sn, and each person has a utility function ui, which is a function from S1 cross S2 cross Sn to R. Of course, there is one most important difference here is that this utility function depends only on the neighbors, myself and neighbors. So it's not explicitly written. You will see it in the examples. So that's the main difference. Once again, you will look at the Nash equilibrium, the same definition what you have seen, and then it's a huge literature on this subject. Okay, existence, uniqueness, and then various structural theorems and learning various questions. Okay. Now, what is the connection with centrality and this network games? Let's look at this first example. So what you do is that you consider this simple game where the utility function ui is given by this alpha I xi plus half sigma I xi square plus summation sigma ij xi x. So when you take, I'm not going to explain you what is the meaning of this particular utility and all. That's not. I'm not looking at that right now. So if you consider this particular utility function, what happens is that if you compute the Nash equilibrium, and the usual thing is the first order conditions you write down, then it comes like that. That's exactly the Kac-Bonac's eigenvalue centrality. So in fact it connects the classical centrality to this network games. This is one it's an extremely beautiful connection between these two things. Okay, now I'll come to one of the my former students' work, which is about the graph coloring. I think everyone is familiar with this graph coloring problems. So let's look at it. Graph coloring is basically you have a network and you want to color the nodes in such a way that no two neighbors will have a same color. This is the thing. Now coloring, this is a very important problem, and many of you may be familiar that this is a NP problem. Now what we worked on about this is that we tried to formulate as a game problem, and it gave us some interesting results. So let's look at it. I'll skip the history of this problem and all. I think I'm also going. Okay, let's start. So the history is basically this problem is started by Leonard Euler, and there is this problem of 7 bridges of Königsberg. When you have this, that's basically the problem, and he formulated this as a graph problem, and that started this entire graph theory. Okay, and then there is a interesting problem here is that this graph coloring particularly it came in the connection of connection with this maps. Can you color the maps? What are the minimum colors required to color the entire map? Now any map you can convert that into a graph, and therefore it becomes a graph coloring problem. And there is a multiple attempts in the history which with incorrect attempts, and finally it is proved by Kenneth Appel and Wolfgang Haken in 1976. But this proof required computer assistance. Even today there is no formally completely mathematical proof with the so-called quote-unquote mathematicians proof. That kind of a proof is still not there, but it is largely accepted proof. It requires a computer assistance of computer to prove. Okay, so now that's basically the history of this problem. Now we wanted to see this as a network game. The network game, what again, all the nodes I think view them as players. Now utility of an agent I in this game is basically this. So basically what I am really doing is this local interaction game is that there is some two-player game. Let's say I play with all my neighbors. Now my utility is simply the sum of the utilities that I am getting over in this network, all my neighbors. That's essentially this sum. So when you take this particular thing here, this is the utility that I am getting by playing with my neighbors, and Aij is 1 or 0 according if whether there is an edge between I and j or not, and I am summing out all my utilities. So this particular game is a little it's a simpler case of whatever network game I have introduced earlier. In the network game it's a general this thing, but this has a very specific type of that. And now again the Nash equilibrium definition is the same thing. This is known as a local interaction game because you are playing with each of your neighborhood locally, and then your payoff is accumulated. Okay, and then in the literature actually Bramuli has studied this particular local interaction games, and he has characterized many interesting properties of that, but we'll go beyond that. Okay, so now we view this coloring problem as a this thing. Again the specific difference here is just this utility function. What it says is that suppose if my color is same as the neighbor's color, then that indicator whatever I have said written there is 1, otherwise 0. So if my color is same as my neighbor, then I am getting -1. If not, then I am getting 0. So this becomes a nice game now. Now once you consider this as a game, and I can talk about this again Nash equilibrium in this game, then what happens is that this is this says that any proper coloring will become a Nash equilibrium, but it doesn't give you whether it is the best or not, because my goal is actually to reduce the number of colors. So in fact this particular thing is studied already by Bramale, and there are some work. Let's not worry about the more things about that. Okay, and in fact so one can actually propose a greedy algorithm based on that game that I have shown earlier, is that we pick a player randomly and let him choose a color which is not there in his neighborhood. Basically you pick any person randomly and he will choose a color which is not there in the neighborhood, and then you keep doing this one. This might lead to this thing. And in fact Kearns and all, they have actually conducted real life experiments to do it, and of course there is a positive probability that it leads to a proper coloring, but eventually the goal of reaching a minimal coloring doesn't work here. Okay, now this is basically the Arco former student's thesis. What he came up with is that instead of just only looking at the neighbors, he also looks at this particular thing. Okay, what he does here is the following thing. So the first thing, whatever term 1 we have seen earlier, is the same thing, and then you look at it. Suppose if 2 of your neighbors have the same color, that's actually advanced, because I want basically to minimize the number of colors. So what you are really doing that in the neighborhood you should have a minimal number. So if any of them have equal color, that adds to my advantage, and then that's why I have put a plus. Of course ki and other things, these are all normalizing coefficients. That's not something to worry. Okay, once you take this one, what you can really do is of course this is essentially what I have said earlier. So this term 2 actually, if you really look at it, this term 2 doesn't really depend on ice strategy. Okay, keep it in mind. So in that sense, it doesn't really change the equilibrium structure from the previous game. So let's, of course, what really happens here is that in the second game, in this game, because of this second term, the Pareto solutions. What is Pareto solutions? I cannot improve without decreasing someone else's payoff. So this is known as a Pareto solution. It's an efficient product. And these Pareto solutions of this particular game turns out to be our minimal coloring. So that's first interesting fact for this game. But this game still doesn't give the this thing. Then this is an example. So what we have done here is, okay, I didn't see instead of this one. Okay. So what we have done here is that now you look at it, it's not just this payoff. I didn't write down the explicit payoff. So what we have defined something called is the neighborhood conflict count. What it says is that given a proper coloring for a player I and her neighborhood Ni, define the neighborhood conflict count as the number of pairs of agents belonging to Ni that have different colors. Basically, you are looking at not just whether they are equal or not, you are looking at the number of different pairs. Okay. Once you take these different pairs, we introduce this as an NCC, neighborhood conflict count, and that what happened is that we could characterize that all those Pareto solutions are nothing but those equilibria which are minimizing neighborhood conflict count. So this is all formally proved, and then again interesting thing here is that the Pareto solutions are not unique. All that one can. Now the next question that finally comes is how do we obtain the minimal coloring? The minimal coloring here is okay. As I said, any game, if you really look at it, one of the biggest problem here is there are multiple equilibria. Like already just in the previous slide you have seen two different solutions. Now the problem that comes is you need to overcome that multiple solutions. So the way we have to come up with some kind of a learning. So because it doesn't have a unique solution or anything, so we need to modify. That modification actually is this one. Okay. So we consider this new payoff. So basically we have defined this Vi is the new payoff, is basically the previous payoff whatever is there plus the neighborhood space. So this is a new local interaction game once again. Okay, from the previous game whatever is there that we are, and now okay, and then okay, I'll skip the analysis part of this one. Once you have this game, what really happens is that you have a nice results. Yeah. So what I'll just directly get into the result. Okay. So every Nash equilibrium will be a proper coloring for this game. There are no improper colorings as a Nash equilibrium. That's the first thing. All the non-proper colorings will be ruled out. And the second thing is that if a coloring is a pure Nash equilibrium of the modified game, then it is a coloring where I player chooses the color most played in her two-half neighborhood. And basically you look at the two-half neighborhood count. Okay. S is a proper coloring where every player is choosing the color most played in her two-half neighborhood. And S is that Si not equals to Sj for all this. So in fact this actually helped us. Basically it is minimizing the neighborhood conflicting count. Now using this one, okay, let me not worry about this. What happens is that, okay, I think what happened is that with this new game you can actually run the best response dynamics. One of the important learning scheme in the games is that best response. What you do is that I take something. What you will do that you will play the best response to my strategy, and then whatever you play, then I'll look at the best response like that. Of course, this is known as a fictitious play algorithm, but there's with little more technicalities. So you can actually do that kind of thing. When you do that kind of thing, what happens is that I'll directly go into this thing. You can really do a very good job here. So the algorithm finally it comes here is that is essentially the coming out from the best response dynamics. Randomly you pick a person, And what you do is that you look at his neighbor and the neighbors of that. What is the color that you play most in that neighborhood, two half neighborhood? I adapt that color. When you do that one, what happens is that you will actually end up getting a reasonably good proper coloring. And of course there is a small issue here is that it still will not be the best, that is the minimal coloring. And in fact it fails when the graphs are not dense. For example, in a tree kind of thing, this might lead to not a very good proper coloring. But if the graph is dense, it in general it works out. Of course it is not like a perfect algorithm, but still it has given a very good algorithm. The advantage of this particular algorithm is that it is polynomial. It's exactly like our Google PageRank algorithm, okay, and it's very simple to implement. In fact, it improves your very fast conversion. Okay, so in fact, when we applied this into many scheduling problems, in fact, it has improved both efficiency as well as time by almost 70%. Okay, that's about the first problem. Okay, I think I'll not go into all these results. The second thing I wanted to mention about the robustness. Okay, when you are looking at these network games, what is really important is that how does this network plays a role here. Suppose if the network, there is some kind of a modification in the networks, then what will happen to the equilibrium structure. So let me introduce this. So the question here is, and in fact I'll give you an application of this particular concept later, but the broader question is basically this: if G and H are two graphs, let's assume that G is contained in H, and then you want to see what happens to the Nash equilibrium of G and Nash equilibrium H. Is there any relation? In particular, the question that we want to ask is that suppose if G is a graph and you are considering a game, now by extending it to H, can I extend the equilibrium of the original game to the equilibrium in the second game? So this is the broader question, and when you take coordination game, it's a very simple game, and then we have some interesting results. I think I'll directly, what's happening? Is it not copied? 1 minute. You can is this possible to connect to this one? Huh? Yeah, I have that. Can we do this here directly? Hmm? No, otherwise I'll just hmm? It's there? Okay, fine. Okay. Okay. Sorry for this thing. Okay. So this question is actually very important because let's say what happens is that given any network, it's routinely we'll see that there are more people may get added, or some people may get deleted, some edges may add, or some additional edges may come. This routinely happens. So in that case, what happens is that is there any possibility that equilibrium also varies continuously? I mean, I use the word continuously in a very vague sense. So it is, in fact, in the standard game theory, this is a very well-studied problem. Like whether you study it as an evolutionary game theory or otherwise, you have a perturbation of, let's say, payoffs or something. It still gives you the good solution. This is the kind of question here. So what we looked at here is that this is a very simple game. It's known as a coordination game, and when you play it on a graph, okay, based on these values of A, B, C, these things, you can show that an equilibrium can be by adding a new edges or removing certain edges, the equilibrium still continues to be. So the results I think I'll skip here because the proofs are actually very simple. It follows from best response dynamics. So I'll not let me not worry about that proofs here. So this is essentially the definition. You want to call a specific equilibrium as a robust, provided it can be extended to another network, let's say G tilde. Okay, that's basically the robustness, and we were able to this. And here the problem is a very interesting thing, because this new edges, how they are being formed. Let's say if I know that who is getting added, where he are getting added, all these details, if I am familiar, then it becomes a complete information. Otherwise, it becomes a incomplete information. Depending on that, the problem becomes this thing. Of course, this is still largely a kind of an open kind of area. So we have some results, but I'll not go into that. Okay, another thing that is very important here is that, for example, what happens is that, let's say there is a new person who is getting added into the network. Now he can choose where to get. Suppose if instead of randomly he is getting added, he may be choosing where to get. So by doing so, he can influence more people. This is like in the computers, there is a very important problem called influence maximization. What you do here is that, given a network, where should you influence so that the spread of, for example, some information will be high. Now the similar kind of question, if for example, let's say if I can choose a position which can affect adversely or maybe positively, whatever it is. Now if I am a strategic, then how does this happen? These problems become much more complicated. So this is kind of an many questions here are open. So in fact, in the slides, I think I will not go through the slides, but you can see them later. These slides are all available. We have come up with some results about this, but my final goal here is I wanted to give you the final application. So in fact, all these problems are open. This thing, I just wanted to give you final this example, which is actually gives this thing. This is, of course, this is just a thought. So I will not say this as a kind of a full question or anything. Look at it. So now we are looking at this financial banks. These banks are there. The banks are interconnected because the banks will have some liabilities to other banks, and also they may also have some earnings through other sources. So now look at this. Now this graph is basically, the nodes are nothing but your banks, and the edges have these weights, basically liabilities. Suppose if the bank I has a liability to J, that's P bar Ij. Now this P is nothing but this matrix of these entries. So all these entries are non-negative. If there is nothing like negative here, only one-sided you are looking at it. Okay. And we are, let's say we are considering only one period model, but if it starts from the day one and at the end of the day it is ending. Now there is also some income that they are getting it from other sources, not from this one. Okay, that let me call that as a C. C is a vector. This is the incomes. Okay. Now the book value of the node I will be this Ci plus whatever money that he will get from the other banks. So that is this first term. This first term is just that. Now this is the liabilities of any node. Whatever I have to pay, these are there. Now at the end of the day, I have to clear all these liabilities. So I can choose to how much to clear each one. So let's say this Pij is what I am trying to clear the liability to the bank J. Okay, Pij is what I am decided to pay. Of course, technically I have to pay entire P bar Ij, but let's to come up with a nice problem, we are just doing it. So Pij is what you are deciding to pay, and now P you take this as a matrix. Then actual inflow and outflow will be basically Pi is equals to Ci plus this summation Pki's, and this will be the how much you are paying this. Now net worth of the bank will be finally Wi is equals to Pi minus Pi. So this is now the question, this P starting with initial network P bar and C, this denotes the set of all possible payment matrices, whatever possible payment, this thing, that condition we have already. Now I want to clearing matrix is basic, clearing solution is basically at the end of the day how much, what is the optimal clearance, how much I have to pay to each bank. So that's you can actually obtain by an optimization problem. This FP is basically an objective function. Specifically, I am not writing it here. What happens is that this interesting thing about this is that this problem can be actually cast as a game problem on the networks. Then you can really look at some interest. Of course, this is currently it's a problem in the conception level, so therefore I don't want to say anything saying that a lot of things can be done. But if you really see this one, this question becomes actually now a game problem on a network. And here is an interesting thing. For example, if suddenly a bank, it is very easy that a bank can go bankrupt. Now in that case, what happens is the network changes happen. Now that's the reason why actually the previous problem, whatever I have suggested, actually becomes an important thing. So this particularly this robust stability and other things become a very important kind of questions. These issues are still largely open. Okay, I think this network formation, anyhow I didn't want to say anything, but the other kind of network games is that how these networks are formed. Let's say I can decide to form a link with anyone, then depending, but when I form a link, I may get some benefit, but at the same time I also will pay a cost. Accordingly, my payoffs are there. Now, given that, what is the optimal network that comes out? And there is a huge literature now, and so I just use this opportunity to at least to give you some ideas of this network games, and using this game theory, you can actually solve some of the complicated problems. So yeah, that's where I think I'll end my talk. And these two are the two books which are wonderful for this subject. Thank you.
Thank you so much, Professor Rao sir, for your presentations. And if anyone have any kind of question, please raise your hand. I guess there isn't. Thank you so much. Your insights have truly enriched our understanding. Moving forward, thank you, sir. Moving forward, we have Surojit Borgakode sir, who will give his plenary talk on his topic, who is more important in a network, the players or a network. I request Ms. Gargi to present her with a small memento. Everyone, I requested to give a round of applause. Sir, please take the stage.
Uh, if I need, I will take. Okay. So this is in continuation of what Malik has already spoken about. But my universe is little bit different from his, because what he was talking about, it was non-cooperative. That means everybody is having a strategy, and accordingly the utility, everybody will be getting the utilities, and some equilibrium concept is being designed on that. But here in my universe, of course there is a network, people are making networks, they will generate some resource, and once this resource is being generated, the question is how to allocate that resource among the nodes or among the players. We would call them players, and in a very fair way, in a very stable manner or fair way. So this stability and fairness is the most important aspect in my universe of cooperative game theory. So this is a network games where I am going to discuss, but at the same time it's all about cooperation. Like people are getting together, people are making coalitions, people are making networks, and accordingly there will be some resource that will be generated, and once this resource is generated, then this resource has to be allocated among the players. I don't have much time, I think, so I will run first. So the title of the presentation is who is more important in a network, the players or the links. In fact, when there is a network, two things are very important. The players means the nodes, and the links they form. So these links mean there is some connection, there is some kind of relationship among the nodes. So we call them links, and nodes are actually players. So in certain cases, I will come up with some examples. In certain cases, you will see the players will be more important. In certain cases, the links are more important, and accordingly, the allocation rule, that means how to allocate the resources, will also take care of. Will have to take care of these links and the players accordingly. Okay. So it's a joint work with my students Sujata and Ellen, and my mentor Sudipta from Virginia Tech, USA. Okay, so this is my problem. As I have already mentioned, a group of players are connected through a network. They will produce some resource, and the assumption is that if some players are alone, they are not forming, they are not in the network, then they will not generate any resource. So to generate the resource, one has to be in the network itself. Then link formation may be costly, or link formation may not be costly. If it is a wireless network, or it's something cognitive radio networks, maybe we don't have a cost involved in the link formation. But if it is a physical network, then the link formation may be costly, right? So we have to take care of all these aspects. I have already mentioned, the problem is to find a suitable allocation rule. And in our area, we have to. This is a theoretical area for the information of our students. So here what we do, we try to find out some allocation rule, and we try to characterize using some axioms. So some characterization needs to be done, that this is the rule that will satisfy these many axioms. These are the axioms with which this is the only rule. So that is what I am also trying to show you. Now the designer is what? He is the God. He tries to design the network, he tries to design the allocation rule in such a way that sometimes he wants to give emphasis on the players, sometimes he wants to give emphasis on the links. So it is the designers, we want to give some control to the designer so that he can decide whether the players are important for this particular game or whether the links are important for this particular game. And these are some network preliminaries. I don't want to spend time on this. This is very standard, and I am If you are interested, you can get it from me. So the first thing is a value function. The value function is it's a function that gives value to a particular network. So the network is being formed, then how to give some or you can say the resource being generated. That value function gives you the resource being generated. And then some component additive value function is to be defined. What is that? Suppose there are different components in a network. Components are like maximally connected networks. So here there is a component, it does not have any connection with the another component. Then the value function will take care of each of these components separately. That is the idea of a component additive value function. Then an allocation rule is something to do with this value function and a network, a given network. So that's why it is a function from Gn to Gn cross Bn means Gn is a collection of all or set of all networks. Bn is the set of all value functions, and y is a function on Gn cross Bn. Okay, and it gives a n tuple. N tuple means it's a vector. It's a vector of n real numbers, and these real numbers will be giving some value to all the players accordingly. Okay, and you don't have to worry about the formula. The next one is the Meyerson value. Meyerson value is an allocation rule. You can see. Don't have to worry about the formula because this is given to us already. It is given to us, and we can compute this value, and we can give accordingly some allocation to the players. But this Meyerson value has a significance. It's a characteristic that it is player based. Like it gives more importance to the players. Like whether a player is inside a network or he is not inside a network, it gives importance on that. And another this one, yeah. So then there are axioms. There are axioms through which this Meyerson value is being characterized. The first axiom is component balanced. Like it does not worry about different components. It will take care of the components separately. Then equal bargaining power. Equal bargaining power is nothing but, suppose I am inside a network and Kaushik sir is inside that network. Suppose I am left with Kaushik, both of us. Then, or maybe I am not in the network. Initially there is a network where myself and Kaushik sir are not there. Then we are being added. Our link, there is a link between me and Kaushik sir, and we are being added to the network. Then whatever payoff I am getting from my network, Kaushik sir will also get the same network. That is equal bargaining power. We have the same amount of bargaining power. That is one axiom, and that is very realistic and very intuitive in some sense. And then balance contribution property, again that is similar to this equal bargaining power, and but it is something like my own power. My own power will be same as Kaushik sir's power, something like that. And then this Meyerson value is being characterized using these axioms, that it is the only network allocation rule that satisfies component balance and equal bargaining power. And the Meyerson value is also characterized by component balance and balance contribution. These are certain properties, these are certain intuitive properties we expect our allocation rule should satisfy. Okay, that's all. Then there is another allocation rule that is called a link-based allocation rule. Here, unlike this Meyerson value, where the player is more important, here the link is more important. And accordingly, this position value is computed. And here, if I have more links, I will get more, in some sense, I will get more allocation, or I will have more resource, something like that. And this is also being characterized by different properties. One of them is linearity. The other one is link anonymity. And there is superfluous link property. That is a very interesting property, in fact. suppose a link is superfluous. What does that mean? That means it does not have any contribution to the link formation or resource generation problem. Okay, then that link is called superfluous. And once this link is superfluous, the players involving the particular link will have no contribution to the network, and therefore they will get 0. So that is the superfluous link property. And then this position value is being characterized using these axioms, and it is the unique allocation rule that satisfies component balance, linearity, superfluous link property, and link anonymity. Link anonymity, let me tell you, link anonymity is nothing but it is anonymous to the links, right? If I have, say, for example, I have say 4 links and you also have 4 links in the same network, our power, our bargaining power, or you can say our contributions will be at par accordingly. So that is link anonymity. Okay, let us come to an example. Like we have 2 allocation rules now at hand. The first one is the Meyerson value and the second one is the position value. The Meyerson value, I repeat, the Meyerson value is purely considering the players, or it gives more emphasis to the players, and the position value gives more emphasis to the links. Now coming to this particular example, suppose this is a network. What is this network? I need this microphone. Thank you. Hello. Yeah. So this is the network. This is, if you are familiar with this concept, then you know that this is a star network. There is one player in the middle, and all the other players are in the periphery. How many players are there? 7. 1, 2, 3, 4, 5, 6, and suppose this is 7. Look at this network. Now you can see player 1 is so central to this particular network, and all the other players are forming links with this particular node 1, right? Now if this is only given to me and there is no game, then everybody would say that 1 is the most central player and it will be kind of contributing everything. Because if we remove this player 2, still there is a network which will be very strong. But if there is a game, there is a value function associated with this, then suppose my value function is something like this. Say this is my whole network, I will call it Z. When the entire Z is being formed, then only there is a value 1. That means if all the players make this particular network where 1 is at the center, then only there is a value generated that is 1. That means if all of them join together, then they will go for the picnic. Something like that. Okay? Then now this 1 is being generated. Now how to allocate this 1 among all these players? Right? This is what the Meyerson value and this is what the Meyerson value and the position value would compute for us, right? The Meyerson value we can see gives everyone 1 by 7, 1 by 7, 1 by 7. And the position value gives player 1 who is in the central, who is the middle. It gives the half of the pi, and the remaining all of them are getting 1/12. Right? So if you look at this value function, without the value function, this position value seems to be more kind of intuitive, right? Without a value function. But if you look at the value function, you can see that even one player, like say for example player 7, if you remove the player 7, that means this 1/7 link will be lost. Then also that whatever in network remains, that network will give no value. because only value 1 is generated when all the players are forming this particular network, right? So who is in the middle, who is in the periphery makes no difference to the network formation, because the value is only generated when all these players are there in the particular network. So from that aspect, this Meyerson value gives a better way. It provides a better way to understand the whole network along with the value function, right? So this is an example where we can interpret that the Meyerson value is a better one, better choice for the designer over the position value. But the whole situation changes when we put some cost of network formation, right? Now cost means, suppose player 1 is like in the central, in the center, so player 1 has to maintain these links with 2, with 3, with 4, 5, 6 and 7. Then this cost will be more for player 1. Then when cost is involved in or incorporated to this particular problem, then value function will be different, but because of this cost, Meyerson value still gives everyone the same amount. But because of the cost, the player has to incur that cost. Then player 1 will be less benefited. And then nobody wants to form the central node, right? Nobody wants to form the central node, become the central node. And accordingly, the network will collapse. And therefore, when cost is involved, this Meyerson value will be not at all reasonable. Then we have to take care of the position value. That means there are situations where Meyerson value makes a better way. There are situations where the position value, that means the link based, I would call the player based and the link based. Player based will give a better better choice, but the link based is a better choice for a different situation, right? So here we have computed, in fact Sujata has computed these things, and with some formulations, you can see with different costs, that means that is being defined by or determined by the kappa, the value kappa. You can see the Meyerson value and position value, how they change, right? Okay. Then there is a third example. So till now we have two examples. In the first example, we have a player based rule, which is more more efficient, you can say. And in the second rule, in the second example, this link based is more efficient. Here is a third example where we have a network, very simple network. It's a complete network with 3 players. Now we can see here the value function, because everything depends on the value function. Now the value function is something you can see. You can see V is, this is a notation. I am coming to that 1, 2, 2, 3, U 1, 2, 1, 3, and minus 1, 1, 3, 2, 3, right? So what is this meaning? What is this expression? U of 1, 2, 2, 3 means it will give a value 1 only when that network has these 2 links, 1, 2, 2, 3. Suppose I am taking 1, 2, 2, 3, 1, 3. Then it is going to give me 1, value 1. Similarly, 1, 2, 2, 3, 1, 2, 2, 3, it will give me 1. But if I take 1, 2, 2, 3, but I am taking 1, 2, 1, 3, sorry, 1, 2, 1, 3, that is giving me 0. That means the first one is giving me a cake, the first one will be giving me a cake when I have in my friends 1, 2 and 2, 3, right? I can be anybody else, but 1, 2, 2, 3 should be there, then only it will give me the value 1. Similarly, it will give me the value 1 when 1, 2 and 1, 3 will be there in the network. It is minus 1 when 1, 3 and 2, 3 are there in the network. 1, 3 and 2, 1, 3 and 2, 3, yes. 1, 2, 2, 3, yes. Now look at this. 1, 2, yeah. Now look at this. You can see this will give me 1, this will give me 1 when 1, 2, 2, 3 and 1, 2, 1, 3 are there in the network, right? So here, who is common in this particular value function? 2 is common. 2 is significant here. Here also 1 is common. 1 is significant. That means 1 has a positive contribution in this case. 2 has a positive contribution in this case. But when they join with 3, 1, 3 and 2, 3, then there will be some negative contribution in the value, right? That means in some sense 3 is a little bit of negative. It has a negative contribution in the game. 1 and 2 have positive contribution, whereas 3 has little bit of negative contribution, right? Then if you look at the network Meyerson value, it does not care about those things, positive and negatives. It just gives everyone 1/3. Similarly, if you look at the position value, it takes care of that negative contribution, and 1 and 2 player 2 half each, but it gives 0 to player 3. So that means position value is very much sensitive about the negative contribution of the player 3, and similarly, on the other hand, Meyerson value is not at all sensitive to the negative contribution of player 3. But if you look at it, you can see this 3 is here also. This 3 is here also. That means what? 3 has some positive contribution in the value function. And similarly, 1 and 2, even though we are talking, we are completely blaming 3 for negative contribution, but 3 is making links with 1 and 2 also. That means what? You cannot say directly that 3 is completely to be blamed always, and 1 and 2 should always get something better. It's not like that. Therefore, this player-based and the link-based, none of them can be a better choice for us in this particular game. And there are many other examples. What to do then? There comes a motivation for us to make a combination of these two. It's a convex combination of this player-based and link-based. That is my proposal. That is my proposal. So here, I am proposing this particular value function, allocation rule. This allocation rule is a convex combination of this player-based and the link-based allocation rule. And now the designer has the control. How much alpha between 0 and 1, how much alpha he decides to give the player-based rule, how much alpha he wants to give to the link-based rule. And accordingly, it's a combination. It will be something between the player-based on one extreme and the link-based on the other extreme. That is the idea, right? And then once this value is being formed, or the allocation rule is being formed, there is a standard way of, justifying that this is the best one. Of course, this is the best one we are proposing, and this justification is done through providing some axioms, providing some characterizations, and that is a purely theoretical part. I think I should not elaborate those things, and these are my axioms. With this alpha combination of this player-based and link-based, I can now compute the values, the allocation values of the 3 players 1, 2 and 3 with the different values of alpha. Alpha equal to 0 starting from alpha equal to 0 till alpha equal to 1. So it is the prerogative of the designer to decide which one will be the best choice for this particular problem. Okay. So lot of characterizations we have been doing. We have done 3 characterizations, but because of time I don't want to spend more time on it. There should be, the axioms should be, whatever axioms we are going to characterize for, they should be logically independent. These are very much theoretical things. We have to find out examples where these are logically independent, and then finally we have 3 characterizations of the particular allocation rule. And there are some future scopes also. We have to talk about the implementation mechanism. That's a non-cooperative approach dealing with the cooperative thing. Then probability can be incorporated, and this hypergraphs, multigraphs, all these things are open problems where we can talk about this type of models. So that's all. Thank you. Thank you very much.
Thank you, sir, for engaging in insightful talk. If anyone has any kind of questions, I guess there isn't. Now we'll have a. Oh, sorry, sir.
I'm
In an example, you can just show alternative things, but in real life, are there any other considerations that might influence my choice of alpha?
Yes, of course, of course. So suppose actually we were working on a particular power grid network. In that power grid network, so two sources of energy is there. So one is like the renewable energy, and the other one is like this one. Now, how much renewable energy you can use in that particular power grid, and how much kind of the other energy, like which is not non-renewable energy. So that can be identified with the help of alpha. Alpha can be some value between 0 and 1. It can be a ratio between the renewable and non-renewable, something like that. Yeah.
So it has to come from outside.
Yes.
So in this case, it could be your priority on the renewable energy.
Yes. It depends on what priority you are having.
What priority you are having. So it needs a context.
Yeah. No, that's why it could be, my approach could be like that, but I thought to give some visualization of the things.
Yeah.